Let's talk about reading assignment 5, section 2.3. In this section, one of the things you've learned is how to sketch irrotational or source-free field for different symmetric problems and also for different problems that are approximately symmetric. Let's start with irrotational field. Irrotational field obviously doesn't have any rotation, but it can have some source rho that would make the field have positive or negative divergence. So if the source is positive, like shown here, rho is greater than 0, then this source will make the field diverge like this. And if the source is negative, then the divergence of the field is negative, so the field will converge instead. Examples of such a field that's irrotational would be electrostatic field or static displacement flux density, which is related to the electrostatic field. And you'll learn a lot about this next term. So the sources in this case would be charges. That's why in a lot of the examples we'll be talking about charges and electric field and things like this. Okay. Let's talk about first geometry, which is a positively charged thin slab. This slab is finite, but it's very large. Here I'm showing the full view, and here I'm showing the cross-sectional view. This charge, let's assume for now that it's positive. Its value only depends on the z coordinate and not on the x or y coordinate. So when I move horizontally, I see the same charge. Okay, so now let's imagine that we're putting our observer somewhere over here. Let me actually highlight the region that I'm talking about. Let's say we're putting our observer somewhere here. So on this diagram, it would be somewhere over here. We know that the observer here is very close to the surface of the slab, and we know that when he or she moves to the left or looks to the left or to the right, the picture looks exactly the same, so the observer wouldn't be able to see the edges of the slab over here because they're so very far away. So what happens is that observer walking on the xy plane in this yellow region wouldn't see any change in the field as a result. So the field would look more or less uniform in this yellow region. So let me sketch this. And again, since the charge is positive, field is going to diverge from the slab and is going to look something like this. And I'm drawing it with the same sort of arrows with the same length and density to show that it's more or less uniform. So this yellow part would be a region where we have a symmetry that would be called planar symmetry. So it's planar symmetry. Region. Now, as we move further away from this region, for example, towards the edges, the symmetry is broken. For example, on this very end, field would look like this, not at all vertical. And then here, it's probably going to be something like this. You would also have, so one reason I'm drawing it like this is because it's going to be something between this and this, but also, you know that the observer will see a lot of positive charge to the right and not a lot of charge to the left. So this charge is going to sort of push the field outwards like this. That's why the field looks like that. You would also break the symmetry if you move away from the surface of the slab. here's why I'm saying this. I don't know how exactly the field would look maybe at this point. I just know it's not no longer going to look like this. But I for sure know that once I move quite far away from the surface of the slab, like really far away, I'm not actually going to see the slab. I'm just going to see a blob of charge. So I know that the field is really just going to look like the field from the sphere because it's just a blob of charge. So something like this. And we also know that the field will diminish as you move further away. So I'm showing it with shorter arrows. In the reading assignment, you probably saw that you can use more, how to say, like infrequent arrows, so less dense arrows to show the field is diminishing. Okay, now let's imagine that we take this same slab, but now we make it very, very large, infinitely large. What's going to happen is that this yellow region is going to become much larger because, well, yellow region is the region where we don't see any change as we walk along xy plane. So if the slab is infinitely large, then no matter where we are no longer going to see any change. And also this region is going to extend up and down as well, infinitely far away. So let me sketch that. So this yellow region is now going to be all of space. And no matter how far from the slab you are, you're going to, when you are moving horizontally, you will see the exact same picture. So it's clear why nothing will change when we're moving in the x and y direction, but actually it turns out that when the slab is infinite, then the field is going to stay the same magnitude when you move up and down as well. You'll soon learn how to explain this using divergence theorem by just computing the field and proving that it's going to be the same no matter where you are. But intuitively, it sort of makes sense because we saw that the field diminishes when you move far away from the slab. Okay, that makes sense. Now, what does it mean far away? Far away means that you are, the distance from the slab is much larger than the dimensions of the slab. Now, if the slab is infinite, then far away means infinitely far away from the slab. This is why everywhere in space you're going to actually see the same field. Now, if this might sound weird because, well, we just discussed field is supposed to diminish when you move away from charged objects. Okay, but think of it this way. If you're on the surface of the Earth, for example, we know that the gravity is supposed to change when you're moving further away from the center of the Earth, but then you don't see this effect when you're close to the surface of the Earth. To start seeing the field diminish, the gravitational field diminish, you actually need to move quite far away. Now let's talk about the source-free field. Source-free field doesn't have any source, which means that it doesn't converge or diverge, but it can have some rotation. Now, this rotation would be created by some flux density J, and to figure out how the field exactly would look like, you would use the right-hand rule. So you would align your finger with the flux density, and then you would look at the way your fingers go, and this is going to be the direction of the field that's created by this current density. So this is how the fingers go. So I'm sketching the field like this. Examples of source-free fields that you'll see next term are magnetic field H and magnetic flux density B. And I think you've actually seen magnetic flux density in grade 12 physics. Now let's talk about some symmetric geometries. And one thing I want to mention is that the way I'll explain things are in a little bit different order and a little bit different than the way it's in the reading assignment. So I really encourage you to go ahead and read the reading assignment to see all sorts of different perspectives. So let's talk about toroidal helix, which is a geometry you create by taking a torus and wrapping a wire like this around it, and then letting some current pass through this wire. What I'm showing below is, is the XY trace of this picture. You see that in the on the inside circle here, this corresponds to this part. You see that the current density comes out of the page here, and on the outer circle, the current density goes into the page. Now to sketch the field, let's consider every wire separately. So you see this wire, for example, would create field that goes by the right-hand rule like this. Same happens to this wire, etc. These wires would produce the field that goes in the opposite direction because the thumb would point into the page. So the field produced goes in a direction like this. Now what you have also is that the field inside the helix is going to be much stronger than the field outside. Here's why. You see inside the helix, for example, this wire produces field like this, and this wire, let's show it in green, produces field like this. So you see that the contributions add. So you get strong F, strong field. Now, outside of the helix, for example here, this guy produces field like this, and here it produces field like this. The blue wire produces field like this, so you see they subtract, and then here it produces field like this, so they also subtract. So outside contributions subtract, so you get weak field. Now we also know that when you go close to individual wires, effects of other wires are not as strong, so you're going to see very irregular sort of field that's dominated by the way the wires go. So it looks something like this. So now I'm talking about what happens when you add all the contributions from the wires. So, and then the same on the outside. But then when you move a bit closer to the center of the helix, you see aggregate effect of all those different wires, so the field looks a bit more uniform. Now let's imagine that we make the windings very, very tight. So let's assume that the helix is tightly wound, which is an assumption that you'll use in the problems you'll be solving. Then what happens is that the effects of individual wires become less important, and those wires sort of create a current sheet. So the field stops being irregular and instead it becomes uniform. Well, uniform doesn't mean constant, but I mean that it stops being irregular and looks sort of like this instead. Now, what you also get is that the field outside of the helix here and here is 0. A way to explain it is this. Well, we know that this problem now doesn't depend on theta at all. The field here doesn't depend on theta. So we only have 3 options inside and outside of the helix. The field can either go this way, it can go this way, or it could be 0. So let's figure out which one it is. So let's imagine we set up a contour, let's say, that passes through the helix. We know that this contour is going to be pierced by a lot of wires. You see all those wires that are coming out of the page here? This means that all those currents are going to create circulation of the field around this contour, which is what we just discussed. The field is going to go like this inside of the helix. Okay, this we know. Now let's compare this to other contours, the ones that don't pass through the helix. For example, this one. On this contour, this contour doesn't encircle any currents at all. This means that there won't be any circulation created on this contour, so the field has to be 0. So here, this contour doesn't get any field. The same thing happens if we set up a contour here. We know that the currents will go out of the page on this part, and then they go back into the page here. So overall, there is no current passing through this contour. So we don't have circulation going this way or circulation going this way. So the field ends up 0. So this doesn't happen. I'm going to cross it out. Now let's imagine that we take this this solenoid, this torus, and we make this radius infinite. What you get is this. So what I'm showing here is this part. This is here, and this would be this infinite radius. So you see how this torus straightens out? So what you get in the limit as r approaches infinity is an infinite helix right here. And then if we want to sketch the field, we can reuse the results we got for the torus. So the field inside would look something like this. And then the field outside is still going to be 0. Now, it's actually not strictly necessary for the field outside to be 0 for an infinite helix, but it very much makes sense. I'll explain what I mean. It's sort of an aside. You don't need to worry about it too much. As far as problem solving is concerned, just assume field outside is 0. But you can technically have some constant field superimposed with f, so some C0 superimposed, and all the governing equations describing the field are still going to be satisfied by this new field. But the thing is that this superimposed field is not going to be coming from this helix. It could be created by some other currents. So not created by the helix. Okay, so this was an aside. Now, we know that field F is irrotational, so it has to form closed loops, but here you don't see this because the loops close at infinity. Now let's imagine a helix that's not infinite. So instead it has some finite length, so it finishes here. Field, field lines wouldn't close at infinity, they would actually close somewhere where you can see them. So the field goes similarly to how it did for infinite helix, but now it comes out of the helix and comes back. Here it looks like this. Now you still actually have a field inside being much stronger than the field outside, because inside of the helix, field from these wires superimpose, and outside the helix, this wire produces field this way, and this wire produces field this way, so they subtract, so still field outside is weaker than the field inside. Now let's talk about delta functions. You should have already seen delta functions in your MAT290 course when you were talking about Laplace transforms. And there is also a lot more details in Appendix C and in Reading Assignment 5, Section 2.1. So what are those delta functions? They are very, very tall and very, very narrow peaks, infinitely tall and infinitely narrow. And when you integrate them, you end up having the area under those peaks equal to 1. Let's see with some examples. In this first integral, you're integrating a delta function from negative 0.1 to 0.1. So in this case, the delta function peak, because it's infinitely narrow, ends up completely captured by this narrow interval, negative 0.1 to 0.1. So when you integrate, you end up with answer 1. Now, in the second example, you're integrating from 1 to 2. This is like this. So you don't end up capturing the delta function peak at all. So the answer is going to be 0 here. In this last example, this is sort of a convention, but it really makes sense. What you have is this. You're integrating from 0 to 1, from here to here. So you actually end up capturing half of this peak. So the area you end up computing is equal to 1/2. Now this last integral, it's really useful when you're integrating in either cylindrical or spherical coordinates. Here, I'll show you an example with cylindrical coordinates. You have here a filament that's aligned with the z-axis, and it has a charge density given by rho equal to lambda over pi r delta of r, where r is the distance from the z-axis. And what you want to do is you want to compute this integral, where v is this red cylinder of height L and radius r. So when you integrate, you'll be using cylindrical coordinates. Z would be going from 0 to L, the height of the cylinder. Theta is a full circle, so you end up integrating from 0 to 2 pi. 1 second. And r is going to go from 0 to big R. Here I copied the charge density rho. Then, really important, you need to remember the Jacobian for the cylindrical coordinates, which is r. So the volume element is r, dr, d theta, dz. So let's proceed with integration. Here you have r and r, these cancel. This lambda over pi is a constant, so it can come out of the integral. You end up with lambda over pi here. The rest of the integral, I just copied all these integrations. Inside the integral, we're left with just delta of r, and then dr d theta dz. Then when we separate all the integrals, here's what we get. Inside, we have integration 0 to r of the delta function, which is exactly what we just discussed. We just talked about this being 1/2. Sorry. And then the rest of the integrations will just give you constants. So this integration will give you L. This integration will give you 2 pi. And this last integration, as we just said, is 1/2. So then 2 ends up canceling, pi ends up canceling, and you're left with lambda and L. So you get lambda times L. Another example is this one where you're integrating delta of x minus 100 from 99 to 101. We know that a graph of a function gets shifted if you subtract something from its arguments. So the graph would look like this. Delta peak would appear at 100. And this would be y equals delta of x minus 100. And you're integrating from 99, so somewhere here, to 101, somewhere here. So you end up capturing the entire peak, so the integral is 1. Another really important property of delta functions that you'll use in this course is the sifting property or sampling property. If you have a delta function that's shifted to some value, like here 100, and it's multiplied by some other function, f of x, and you integrate, let's say from negative infinity to infinity, what you end up getting is the value of the function at the location of the peak. So you end up with f evaluated at 100. Now let's do problem 1 from section 2.1 of assignment 5. You are given charge density rho as a function of x, y, and z equals to lambda delta of x minus 3 delta of y plus 4 coulombs per meter cubed, where lambda over here measured in coulombs per meter is a constant. In part A, you're asked to compute the total charge enclosed in a box that has dimensions of 0.2 by 0.2 by L, and it's centered at x equals 3 and y equals -4, and z can be any height. So to find the total charge, we want to integrate this charge density. Here I copied this expression. X will go from values that go around 3, and they need to be 0.2 apart. So this would be 2.9 to 3.1. Y would need to go from -4.1 to -3.9. And z would go, well, we can start it at 0, and then in that case we need to end it at L. Lambda, which is a constant, comes out of the integral. Then you see that this only depends on x, and the integration is constant, and then the same for y. So we can separate the integral into 3. Here is the same limits, 2.9 to 3.1, and then delta x minus 3. Here we have limits the same as here, and this delta is copied, and here is the integral from 0 to L and dz. Now this first integral, what is it? We know that this delta peaks at x equals 3, right? Peaks at x equals 3. And the integral captures this value. So this integral is going to be 1. This delta peaks at y equals -4, and this integral captures this value. So this integral is also equal to 1. And this last integral is L, so we end up with lambda times L. Now let's double check the units. Q is charge, it's measured in coulombs. Lambda we were given is in coulombs per meter. And L is measured in meters. So meters cancel, so this means the units make sense. In part B, you're asked almost the same thing as in part A. The only difference is the way you center the box in terms of y. So here y is going to be 0. So the integration is the same as here. The difference is the y limits. They will go from -0.1 to 0.1 because we're centering it on 0 now. Again, separating this integral, we end up with these bounds going from -0.1 to 0.1. So this integral in the middle, instead of being 1 like it was here, it's going to be 0, because this delta peaks at y equals -4, but the interval doesn't catch that interval. Sorry, the interval doesn't catch -4. So this overall product is going to be 0. Now in this part, you're asked to describe the geometry of this object. So it would be the location of the object and also which axis the object is parallel to. We know that rho of x, y, z is only a function of x and y. So we have rho of x, y, z equal rho of x and y, which means that, that the object extends infinitely in the z direction, because no matter what z we plug in, we see the same charge density. We also know that rho is infinite when x equals to 3, and y equals to -4, which are the values at which both of these deltas peak. So both of these deltas are infinite at those x and y. So this means that the filament is parallel to the z-axis, and it's located at x equals 3 and y equals -4. Now, I should also mention that that we've verified that if we set up a box over here at x equals 3 and y equals -4, we end up capturing some charge, which is equal to lambda times L. This was in part A. Charge equals lambda L. Now, when we change x and y, so we make this box miss this, this place that we claim is where the filament is, we end up with 0 charge. So this is sort of a sanity check. And one of the reasons it's nice to do this sanity check is because here the argument was had to do with multiplying infinite numbers with, let's say, when y is not equal to -4, this would be 0, but then this might be infinite if x equals to 3. So a better way to understand what's happening in that case, instead of talking about 0 times infinity, is to see what's happening to this box in capturing charge. Okay, next part. Next part asks to find linear charge density in coulombs per meter. And we found that if we set up a box that will carve out L meters of this filament, we end up capturing lambda times L coulombs of charge. This means that linear charge density, which is the amount of charge per unit length, is equal to lambda times L divided by L equal to lambda. And it's measured in coulombs per meter. So this means that we can actually just read off the geometry of this filament and the property like the linear charge density just from this expression. And you don't have to redo this computation every time. You can actually just look at this and you'll know that the charge density is equal to lambda. Now let's do a problem at the end of section 2.4 in assignment 5. This problem involves a charged cylinder, which is shown in orange. It's parallel to the x-axis. You also have a charged slab, which is this pink object here. It's also infinite. And you want to find the field at the center of the slab, right here. Now you see that this problem is not symmetric because it neither has cylindrical symmetry nor planar symmetry. So it's actually pretty difficult to even sketch the total field. But what you know is that if you break the problem down into two parts, one for the cylinder and one for the slab, then the problem, each separate problem becomes symmetric. So it's, as you learn soon, it's not going to be too difficult to solve for the field produced by the slab and by the cylinder. And to get the field in the original problem, you can add up the field produced by the two objects. And this is called principle of superposition. You'll soon learn how to find the field from each object, but we already did this for you. Here you're given the field for the cylinder, F1. I'm going to sketch this in orange. It's going in the radial direction from the cylinder. So something like this, both outside of the cylinder and inside of the cylinder. This would be field F1. And the reference point for this field is 0, 0b instead of the global origin. Because when you're solving the problem for the cylinder, you treat this point as the origin. You don't treat this as the origin. So in this case, r, for example, the cylindrical coordinate variable would be the distance from the axis of the cylinder instead of the global x-axis. So distance from the axis of cylinder instead of this guy. Let me show you. So the x-axis goes here, but that is not the reference point. That is not the axis from which you count r. Field from the slab with respect to the center of the slab is given by these expressions here. For the three regions, one region is local z above d over 2. The field is going upwards there. This would be F2 from the slab. And below the slab, it's going to be negative z hat, so it's going down. Inside the slab is going to be a function of z, so it's going to go like this here, and then for negative local z, it's going to go like this. And then what you want to do is you want to understand how these two fields contribute to the field at this point over here. What I'm showing you here is I just copied down the field from the cylinder and the field from the slab here. To solve this problem, the first step is to convert everything into Cartesian coordinates. Let's start with field F1. We need to write r in terms of x, y, and z, and do the same thing for our hat, and do this inside and outside of the cylinder. So let's see here. We know that this problem, instead of having x here and having y here, and the cylinder being aligned with the z-axis, instead the cylinder is aligned with the x-axis, and here we have y and z. So y and z, it's sort of like x and y in the way you're used to seeing these problems of converted coordinates. So let me draw this here. We have y here, we have z here, and we have x-axis coming out of the page. Oops. I don't actually know how to put this circle here. Okay, this is gonna have to do. Okay, now this I'm going to copy on the next page. So you see that our variable, which is the distance from the x-axis, is now square root of y squared plus z squared. Our hat, we're used to seeing it as cosine theta, sine theta, and then having 0 z, z component, but now it's a little bit different, but very similar. So it's going to have 0 x component, then cosine theta for y, and sine theta for z. Now theta in this case is counted from the y-axis, not from the x-axis like you're used to. But this is in terms of theta, and we don't want that. We want everything in terms of x, y, z. So we get 0 y divided by square root of y squared plus z squared. And then we have z divided by square root of y squared plus z squared. And in assignment 0, you'll see more details about how to get this r hat. Now I took this field and plugged everything in. You see this was r here. R hat is over here. I just copied it down. And then this term is the same thing as here. This was for the field outside the cylinder. This part is just this r replaced with what it is in terms of x, y, and z. The same thing for the field inside the cylinder. This again is r less than big R. This r becomes this. Here we have our hat. Then I simplified things a little bit. I took this part and shifted it out of this vector. Then this loses the square root as a result, and we're left with 0, y, and z in the numerator. For this field, I canceled this with this factor here, so I end up with 0, y, z divided by r squared. Now to remind ourselves, this is not with respect to a global origin. This is with respect to the point 0, 0, b, which was the center of this cylinder. Now for field F2, we can just copy it because it was already in Cartesian coordinates. So here I just copied everything. Oops, sorry, there is a mistake. This should be minus. Okay. And this is with respect to the center of the slab. Let me put it in pink. So this would be 0, 0, negative a minus d over 2. The next part is to get the total field at the observation point. But the complication is this. The field we found here and the field we found here is with respect to different reference points. So we can't just add the two things together because x, y, and z mean different things. Well, x and y mean the same thing, but z means a different thing because the two reference points have different heights. For example, z equals 0 for the slab means this center plane of the slab, but z equals 0 for the cylinder field is going to mean this level. So now we want to figure out what each of these fields is equal to at this observation point. So we want to figure out what to plug in for x, y, and z if x, y, and z are local coordinates instead of global coordinates. So here I wrote this more formally, that x, y, and z in the fields above are some local coordinates that are with respect to two different reference points. The reference points would be these guys. And we're interested in finding the field at the observation point, which is the center of the slab. Observation point is in blue, would be 0, 0, negative a minus d over 2. Now to find this, what you want to do is you want to take the observation point and subtract off the reference point. Let me write the formula, and then we'll do this for every point, and it will become much more clear. So local x, y, and z is equal to the observation coordinates minus the reference coordinates. So x minus x reference, y observation minus reference, and z observation minus z reference. And these are the values that we would plug in for these local coordinates that we have here. So for example, this z. Now let's use this formula to find fields f1 and f2 at the observation point. Let's start by computing f1. We have the reference point for the field f1 at the center of the cylinder. So this would be 0, 0, b. This means that the local coordinates would be the observation point minus the reference coordinates. So the observation point minus coordinates of this point. So this would be 0, 0, and then this minus this. So negative a minus d over 2 minus b. Now we would get the same value, the same point if we just look at this diagram and realize that this is the local origin. So local 0, 0, 0. And we want the coordinates of this point with respect to this point. This point is this distance below this point. What is this distance? This is b plus a plus d over 2. So a plus d over 2 plus b, which means that the local coordinates of this point are the same as this, but a different z. So 0, 0, and then negative a minus d over 2 minus b, which is exactly what we got here. Now there is two regions for f, right? There is the region outside and inside. And let's choose right away which of those expressions will plug these x, y, and z into. The observation point is here, so it's outside the cylinder, which means that we choose this expression instead of this one. I wrote this formally here. I replaced y and z here. I wrote subscript local to differentiate between y and z overall global. And we're choosing this expression. We can also check that this is the case by plugging in the local coordinates of these points, which are here. Let's plug them in. And we get y local is 0. This is z local. Let me show you here. And then this 0 goes away. And then this square and this square root makes this absolute value of this quantity, which is a plus d over 2 plus b. This is greater than b, which is greater than r. You can see this from the diagram. B is greater than the radius of the cylinder. So our guess was correct. Let's use this to compute field F1. We are choosing this expression, which is 0, y local, z local, divided by y squared plus z squared. So this would be 0, y local, z local, divided by y local squared plus z local squared. This simplifies because this factor and this factor cancel, and we get 0, 0, 1 divided by negative a minus d over 2 minus b. We can factor out the minus and write it as 1 over a plus d over 2 plus b z hat. This is equal to negative 2 divided by 2a plus d plus 2b z hat. Let's do the same thing for the field F2. For the field F2, the reference point is at the center of the slab. So this is equal to 0, 0, negative a minus d over 2. So the local coordinates of this point we get from this formula. We take the observation point and subtract the coordinates of the reference point. So the observation point, actually, we get 0 minus something. We get 0 minus something again here. And then here we get negative a minus d over 2 minus something. Then we subtract the reference point. We get 0, 0, and here we get minus a minus d over 2. Then this 0 and 0 cancel. We get 0. Here we get 0. And here again we get 0, because this and this cancels. This also makes a lot of sense, because if we just look at this, this is the observation point and it is the reference point. So the observation point is exactly where the local 0, 0, 0 is. This is observation point. And this also happens to be the local origin, which is what we got here. Again, we have different regions. Here we have 3 regions, 1, 2, 3. Which one do we choose? Well, the observation point is inside the slab, so we should choose the point where the local z is between the 2 heights of the slab ends. Then we want to compute F2. We are choosing this option. This is 2 over d, z local, z hat. I wrote it here, 2 over d, z local, z hat. Z local is 0. So then we get 0 vector. Then the last step is to get the total field here. We found this as the field F1, and we found this as the field F2 at the observation point, and here I just added the two things together, and this is the answer. That's all you need for this problem. So it's done. A few more things I wanted to mention is this. In step 1, we converted everything to Cartesian coordinates instead of, let's say, cylindrical. So what I want to do is to justify why it's a really good choice for this kind of superposition problems to use Cartesian coordinates instead of other kinds of coordinates. At the end of step 1, what we had is local expressions for the vector fields in this form. We had some x component in terms of x, y, and z, x hat, plus some z component, some y component in terms of x, y, and z. All of these were local. Y hat plus z component, x, y, z, z hat. You might not recognize this by looking at it, but let's see here. This was at the end of step 1. You see we have this would be the x component would be 0, for example, for F1. Y component would be y divided by y squared plus z squared. Z component would be z divided by y squared plus z squared, etc. So here I wrote them like this in terms of the unit vectors instead. Then in the next step, we needed to take these component values and evaluate them at the observation point. Now, if you instead, at the end of step 1, had, let's say, cylindrical representation of the vector fields, then you would have local fr as a function of r theta x, r hat plus f theta as a function of the same thing, theta hat plus fx times x hat. Now here things would get more complicated because you need to evaluate these, so that's as before. You need to evaluate at the observation point, but also, let me first write this. So you need to evaluate these at the observation point. But also, you would need to understand what this r hat, theta hat mean at the observation point. And this can get a little bit tricky for a general problem. The reason why is this. Let's say your reference point was here and your observation point is here. When you write r hat locally, it means this, right? So this is r hat local. This is what you would have had at the end of step 1. Then this loses its meaning when you stop talking about this reference point. So, for example, when you're back to talking about the global origin, r hat just means this vector. So this becomes meaningless, and you need to convert this either to global Cartesian coordinates, so this r hat, or go back to Cartesian coordinates. And then if instead you use x hat, y hat, z hat, you don't need to worry about this at all. That's why this whole issue of converting unit vectors never came up in the second step. Another thing I want to mention is that you didn't have to go through as many steps for this particular problem, but the approach that I described here and that was described in the reading assignment, it's really general, so it works for any observation point. But for this problem, you can sort of look at the diagram and figure out what the field is supposed to look like. For example, for field F1, we needed to get local R, but we know that local R at the observation point, let me actually do it in orange. R local of this observation point is equal to this, which is A plus D over 2 plus B. Then we needed our hat local, and this you can actually, for this problem, get it from the diagram, because at this point, our hat local just points downwards like this. You see this our hat local here, and this is our hat local at this point. So what is this? This is just negative z hat, right? Because it's pointing downwards, and it's a unit vector. Then plugging everything in for the expression of the field outside. Remember, this was outside the cylinder. We get negative z hat, and we have 1 over r local. And this is exactly the expression we got. If you multiply top and bottom by 2, you will get the same expression as we got here. For F2, we needed local z, but local z at the observation point is just 0. And plugging in everything for the expression of F2 inside the slab, you end up with 0 vector. When you add the two things together, you get the same answer as we got by doing those more general steps. So same answer.